that has
Yes.
been a challenge. But for the most part, yeah, I've enjoyed coming to back to school. So
Just as a tip, since you talked about it, being a graduate student, so one of the best strategies that kind of balanced out across the different classwork and also your priority. I just have a strong feeling that both Rahar and you, both of you, may end up with a thesis option. We never know, but if you do that out of those all class work in your own research, even you're preparing for the doctoral program later, and just think about different time management. And I think that is the most important thing. And different classes had a usually different schedule, but sometimes, unfortunately, faculties feel maybe this is around the right time for us to have something to do. And also sometimes some weeks are busier, some weeks are better, but I hope you're doing fine. But regarding our, just class as well, and next Tuesday is the due for the literature review. But again, just since we have only just a few students here, Rahar wanted to find a better data set. So maybe he can just thinking about different directions or different topic, maybe eventually. But anyway, just to making sure that the 14 different articles or book chapter you just just for your research paper you are developing in this course. But any hypothesis you're thinking of right now, so at least we can discuss either good hypothesis or the problematic hypothesis, so we have a better sense of it. Do you have any hypothesis in your mind right now? Heard?
mm,
Dylan?
I mean, kind of, but with everything that I've been like looking up, I think
Mm-hmm.
like so far, like I guess my general idea is that war hawkishness amongst a population is not necessarily affected by uh, belief about economic well-being.
Okay. Okay. So I know Dylan's research questions. So far, it's just the beauty, right? How those economic factors can drive some of those perspectives about hawkish. So, in other words, more of the realist approaches in international relations. I don't know. Maybe we can put out different wording on it. So there uh, always some international conflicts and some of the decisions we make, a lot of things are economic driven decision as a capitalistic society. So it is a theory driven, yes, it is. And then as long as Dylan is dealing with some of the economic variable about their expectation about their well-being or their socioeconomic status and how they see the world view out there, is that possible? Yes, AS data set and GSS data set, they already ask the questions. That's measurable. People answer to the those questions that are measurable, right? So that is a great hypothesis. Why not? Why not? Okay. So I'm sure you found quite a lot of studies to just kind of dealing with different studies here and there, but hopefully you can find the exact something. There are like to be honest with you, if you cannot find the exact study you wanted to do, it's a good thing. It is a great topic you can pursue for your thesis and doctoral dissertation, because the study, there's no really single source study done exactly what you're doing. So it's a great potential study, but at the same time, in order to do that, you need a lot of crazy, like just like motivation and all those effort you put in collecting all the theoretical perspectives, pull it out from that. And somebody haven't done it, and it's a challenging work, but that's something great about something really never done it before. All right. Okay. So anyway, that's a hypothesis. Thank you for the great example, Dylan. So hypothesis test, the definition wise, it is a statistical method to explain what you want to know about the population of your research interest. Your research interest can be not U.S. census, right? But if it is about international, the conflicts who are involved in, then that's that group. And people in minority, if that is your research question, that's the subset of the really all the total population. But here, so whatever the population of your research interest, we don't know about them. There's no way we can find everything about them. So we collect sample, hopefully it's the most representative, and then using the sample, we try to explain something about the population. So it is a statistical method to doing it. That's a hypothesis test. Okay, so now let's move on to just some of the assumptions. Okay, assumptions of a hypothesis test. Okay, so can you do hypothesis tests for only quantitative research? Or we can do qualitative research, or maybe sometimes a case study. Yes, you can do case study, quantitative research, qualitative research. You can do all types of data for hypothesis tests. Okay? So it's sometimes a case study have one or only two case, but you can still prove and disprove what you brought as your hypothesis, right? But most of the hypothesis testing statistics, it is a quantitative data, most of the case, okay? And then, but just you need to understand, throughout the semester, we're gonna cover different statistical method. And different statistical method use different distribution. Like as what we covered last week, we now know only one statistics and one statistical distribution table, which is a Z, normal distribution table, right? So we know the normal distribution table is likely most likely to occurring incident in our research, because whatever we do, majority of cases and samples, they ended up in the most frequently, and less cases it goes beyond the tail side. So it's most reflected the variables and then some experiment and observation we do, but making sure that we just only know by numerous experiments with the numerous the sample studies, right? But still, we don't know 100% about the population. There's no way we can do, right? So they are again, when you do hypothesis test, we assume that it's random, it's most representative. So we assume that most of the possibilities are in the center, and less possibilities are at the tail side. So those are some of the logic that statisticians they decide to use for hypothesis tests. Regarding sample size, okay, as we move on from for example, t-test, that's what we're gonna cover next week, okay? In order to do the basic t-test, whether your sample is different from your population, also t-test is the statistical test when we compare two different groups. If you compare two different groups, what is the minimum sample size in order to have reliable result? All vary by different statistical analysis. So for example, if you look at the sample, total sample, and see whether they have any statistical meaning, whether it's statistically significant or not. The minimum sample size, again, goes back to central limit theorem we covered the last week, okay, last class. So we need this minimum sample size of 30. So, and then gradually your sample start to represent, and we can put it the normal distribution table to test it. And if you compare two separate groups, you need at least 20 cases in each group. So 20 males and 20 females, and then you can compare. If it's less than that, it's not reliable t-test. Okay, so each statistical analysis require a minimum sample size. It's not a lot, but I will sometime, if it is not today's class, but on Thursday class, I will tell you most of the solution for any problems or statistical analysis is to increase sample size. I will tell you why later, okay? That's like a basic structure of statistical formula, okay? Again, you guys just saw that. Although it's a formula, but it's not really formula. They just statisticians try to show what they try to do, right? So using the unit as standard deviation, so they divide it by standard deviation, something like that. So it's more of those expression that statisticians they decided to use as a logic. All right. So the first step of doing hypothesis testing is writing out hypothesis. Okay, hypothesis. But here there's two hypotheses, two types of hypothesis, but for same purpose. I wanted to go over for next maybe 2, 3, 5 minutes. All right. So hypothesis is the very first step, how you start statistical analysis. Okay. In order to prove it is statistically significant or not. When you write a hypothesis, you can write in two different ways. The first hypothesis, first way is write up the hypothesis talking about no effect, no relationship, no change, nothing going on. So as what the definition is saying, as the name say, the null hypothesis. The hypothesis state about insignificance. Okay, nothing happening, no relationship, nothing. Okay. That's what statisticians they decide to test. Okay, just wait for that. Okay. But alternative hypothesis is something it's a state about there's a relationship. That a medicine has the effect. Vaccine had a problem, side effect, so let's just throw away. Whatever the argument they make, okay? Something it's about change, relationship, effect. Think about it. That's what you want to prove in real world research question, don't you? Right? So that we call that as alternative hypothesis that are actually contradicting null hypothesis. Null hypothesis. So null hypothesis is what statistical analysis actually testing, but what you actually prove is alternative hypothesis. I will come back to this, but just wait for this logic. You don't need to write up anything. This is all from the textbook for next 2-3 pages, so don't worry about it, but just try to understand. Why we test null hypothesis? That is not our interest. We want to prove alternative hypothesis. Mostly there's effect, the relationship, and the changes and things like that. But the logic they choose was it is much harder to prove something is true, right? It is much convenient to prove something is a force, right? It's a logic. And as the textbook really talked about it, if you want to prove swans are white. Okay, let's say me, Dylan, Rahul, we go over all over the world, different part of the world, and timelessly and everywhere. Okay, so find all white swan and just okay, they are here in Africa. They are all white swan, all here white swan. So prove things are true. It takes a much longer time because you need to go over every cases, every possibility. But if you find one single case of the force situation and force a case, then you're done, right? You disprove it and you can confirm, okay, this is a failing, so the other opposite statement is correct. So that's the statistics of logic they wanted to use. Right? So when your null hypothesis is a force, which is easier to prove, and then your alternative hypothesis will be proved. That's the logic they use. That is why they test the null hypothesis just to try to prove there's a force evidence. And thus we can argue your alternative hypothesis is proven. Okay. By the way, have you ever been San Antonio Zoo before? Anyone? If you don't, go and find black swan there. There is a black swan in a San Antonio Zoo, so you can easily falsify just right here in about 1 and 30 minutes away. You can find that all the swans are white. That's a falsified statement. So we can reject it. So and thus we can make alternative hypothesis proven. So this is the logic. So we test the null hypothesis to falsify it, and thus we can prove our alternative hypothesis. Okay? So that's the logic they use. Are you with me so far? Okay? So eventually we're gonna draw the null hypothesis in the probability distribution. So we wanted to see pretty much no evidence of that, no proof. So that's where you set some of those criteria to disprove it. And thus we can argue that our alternative hypothesis is more likely, so we can prove what we wanted to prove. Okay? So the second stage is just what I kind of hinted here. And so we need to set some criteria up to a certain point. At what level of the error or evidence we can falsify our null hypothesis. Okay, so that's alpha level. Okay, in statistics, I will just give you that some numbers in a bit. Statistical software, they consider that, right? Mostly less than if we do the statistical analysis, the chances are less than 1%, or the chances are closer to 0%, or the chances are the maximum no more than 5%. That is a conventional alpha level. Statisticians, I didn't decide, but statisticians, they decide, okay, so as long as our null hypothesis stay in those 1% or 5% level, we can falsify it because it's a very low probability to occur. So instead, we can prove our alternative hypothesis, which is the opposite statement of null hypothesis. So I'm sorry, I actually already, what I just said is already stage 3 and 4. Okay, so I went ahead of time. Just to give you a hint a little bit why. Okay. So second stage, we set criteria. So up to when we can reject null or still accept or fail to reject null, or embrace is still null hypothesis. So where is some criteria? So that's alpha level. When we gonna cut it off? Acceptability or denial of null hypothesis. Okay, so alpha level usually in academic work and statistics, it's less than 1% of a chance, less than 5% of a chance. Then usually in statistics, regardless of whatever statistics you do, we reject the null hypothesis and accept your alternative hypothesis. Okay. So that's alpha value. And the p-value, you already know, it's a probability. But as what we discussed last week, we will cover different statistical distribution, okay? T distribution, chi-square distribution, apple distribution, based on each corresponding statistic value. So for example, normal distribution for specific z value in a normal distribution table, there is a specific corresponding probability, right? That's a p-value. So if you plug in those statistic values, your mean value, your population values, standard deviation, whatever the value you plug in, they will provide you statistic value. To those statistic value, there are always a corresponding probability. That is a p-value. Okay? So if that p-value from statistical analysis is very small, less than 1% or less than 5%, so it's beyond the alpha value set, 5% or 1%, whatever it is, then we can reject the null hypothesis. So eventually, hypothesis, the decision is depending on your alpha value, where you set the criteria, and where is your statistic value and corresponding p-value. Okay, so p-value is from your statistical analysis, and we just need to look at that p-value is in the beyond the critical alpha value or inside of the alpha value. I will show you in a normal distribution, tape shape, so you can understand it better. But now at this stage, just understand that we set either 4% or 5% for criteria, and that p-value, it will be calculated by statistical software most of the time, okay, based on the sample. Okay, so we just know where is a p-value outside or inside of the alpha value, beyond or inside of the alpha value. So just let's think about the connotation of that. Okay, when your statistical value of z is pretty high, and then so corresponding p-value is 0.001. Okay, so the probability, as I mentioned, that we want to use null hypothesis to prove it, and whether you telling you really notify statistical software what is your null hypothesis or not. Statistical software, by sort of pre-agreement, okay, pre-assumptions, they already know no changes, nothing going on. That's null hypothesis. That's what they test. That's the probability provided for those null hypotheses. Okay, so this is a sort of pre-agreement already done. All right, so do not get upset. Okay, I want to tell software, this is not null hypothesis is not what I wanted to do in the conventional way. I want to do different way. Then actually there's a way. There is a statistical kind of the software. You can actually write for statistical analysis. We call that R. Okay, then you can really some change it that your hypothesis manner, but still what they will provide you based on you plug in, and I will do regression model, chi-square model, and they do regardless of you are telling them or not, regardless they test something is not meaningful and not changing, no relationship, what is the probability? That's what they will provide you. So small p-value for null hypothesis, it's very unlikely to occur. So like less than even 1%. So you reject the null hypothesis, which assume that there's no relationship, nothing going on. So you can confirm alternative hypothesis actually that medicine work. There is a relationship, there is association. That's what you can argue at the end. But like when you do statistical analysis, having corresponding p-value from statistical analysis, you got the value of 0.26. That means your null hypothesis had a 26% chance it is still correct, right? 26%. It's quite a lot, right? You are not able to reject null hypothesis. Okay. In that case, you failed to reject your null hypothesis, and thus you also failed to prove your alternative hypothesis. Okay, so when you have a high p-value, that means mostly there's some um, limited information. It's maybe there's no effect, no significance. That's how you can interpret with the p-value. Okay. So regarding additional information about alpha value, we also call that as a critical region. So we're gonna cut off what is the percentage that we can reject or accept our null hypothesis. As I multiple times mentioned that in statistics, even statistical software, they will automatically know SPSS unless you change that to 0.01, less than a 1% chance. But by default, they set as a 5% chance. If your null hypothesis has a less than 5% chance, they reject null hypothesis. Okay? So that's how statistical software and statistical analysis is set before you do, right? So but if you want to be more rigorous about analysis, you want to make sure that it should be less than 1%, more rigorous. Okay, you can do that, but conventionally we do 5%. If we continuously practice and continuously done research, prove that null hypothesis has a less than 5 chance to occur, then you can reject it. All right. So the decision is up to where your p-values are in distribution based on the step value of alpha value. Okay, so let's look at this graph. I actually brought from the textbook. Okay, so it might be easier for you to follow. Here, so if our null hypothesis, it is normal distribution, right? If a null hypothesis has a lot of chance at the middle, okay, 25%, 30%, 50%, you cannot reject null hypothesis. But we said here, this is alpha value, alpha level, that most of the time we set 5%, or if you want to be more rigorous, push that to the end, maybe 0.01%. I'm sorry, 0.1% further down there. So here you see the blue area. That's actually critical region where you reject null hypothesis because the probability for null hypothesis is low. So you reject. So alternatively, what you can do, you prove your alternative hypothesis. So you prove what you want to prove right here in this critical region. All right. So these are identical. sometimes like a chi-square or alpha distribution, their shapes are a little different than normal distribution, but the tails are still tails. All right, they still have a critical region based on alpha value. That's all those decisions are go. Okay, so this is what we call as a critical region. So, and that within that region, you can reject the null and prove your alternative hypothesis. Again, we are using null hypothesis to prove your alternative hypothesis. Okay, so any question up to this point? Any question? So you understand the statistics and the logic, why they, okay? I know. So this is more of the, not really, it's a scientific. No, it's a social science. They believe that this is a better way to talk, but that's what they decide. That is why it's all in the statistics textbook. Okay, so now let's just try to understand their logic. That's what we're gonna do. So, the stage 3, we do statistical analysis. Okay, so here this is the flexible part of statistics. So depending on your hypothesis, you can run z-test, t-test, f-test, or chi-square test. Whatever the test you're gonna run, you need to decide based on your hypothesis and scale of variables, number of variables. And that will be the practice we're gonna do for the second half of a semester thoroughly. Okay, so don't worry about it. But like now we just only know Z test and Z normal distribution table, right? So let's say that we done Z test and then we find the corresponding p-value, so we wanna test it. So let's say if you have larger z value. Okay, let's go back here. Larger z value, so goes farther away from the center. So larger as you goes out, as what we practice in normal distribution table, further goes out to negative or positive side, the statistic value goes up, right? The by statistic values goes up, z values goes up, the probability goes down, right? Okay, so high statistic value, low probability, it's a good thing because you can reject the null hypothesis and thus you can prove your alternative hypothesis. So this is the question I quote from the textbook. So small value of z-score, z-statistics is evidence that the null hypothesis should be rejected. Is that true or false? So in other words, if you have a smaller z value coming toward to the center, it gets smaller because at the center, the z score is 0, right? So you are more likely to reject null? No. If you are here, there's a lot of probability, a lot of chance that your null hypothesis is still correct with that much probability. You cannot reject it, right? So small z value, you are not likely to reject the null, and you are less likely to prove your alternative. So this statement is false. If you have a large statistic score of z, and thus you have a small p-value, you're more likely to reject the null hypothesis. That's correct. You got that? Okay. So this logic is the same across different statistical analysis with a different statistic distribution. Okay, so now the last stage of the hypothesis test. Again, it's all identical process. Whatever you do, the logics are the same. So you set alpha value, and your p-value is a critical region. You reject the null and accept alternative. So and thus, it is statistically significant. If your p-value is in the body, it's because it's too big, it's larger than alpha value of 0.05 or 0.01, then you fail to reject the null hypothesis because your null hypothesis is still very much a high probability, right? So you fail to reject the null hypothesis. So you just look p-value and alpha value, and whether your p-value is in the body or in the critical region. If it is your critical region, you reject the null hypothesis and you prove your alternative hypothesis. That means it is statistically significant. That means your null is wrong. There is some effect, changes in relationship. Whatever you do as your research question. Okay. So p-value is smaller than 0.05 and 0.01. Then finally, we reject the null, falsify null hypothesis, and proving your alternative hypothesis. That's the decision how you to make across all different statistical analysis. Okay? Not only Z distribution and hypothesis test, but anything. Any statistical analysis in the market you do, same logic. Okay, so that is why I'm saying it is the foundation. You got that? Okay. Any questions so far? Okay, so eventually, what you needed to know in order to finalize your decision in statistical decision, whether it is statistically significant or not, just to know the probability from statistical analysis and whether the p-value is in the body or in the critical region. Okay? In the critical region, the probability is smaller than what you set as a criteria, so we can reject null. And then in the body, probability is too high for null hypothesis, you cannot reject it. Okay? So that's how it is. So let's go to, since we only learn Z normal distribution, right? And a Z table is a particular, we know exact statistic value. And from exact statistical value, there's always the exact corresponding p-value. But don't get upset, all right? From now, any other statistical distribution and Dale table, actually, the p-value is depending on sample size. You must be crazy. No, okay? So beyond the normal distribution, any other distribution and any other statistical analysis, their statistic value and corresponding p-value changes by the sample size, but the normal distribution, same. All right. So either you know Z value or the corresponding P value, you know, like large enough Z value, either negative or positive, means you know the P value at Z value of 1.96, it's a 0.5, both sides. Okay. So you can reject null. Okay. So it's pretty much if you know statistical Z value or P value, you automatically can decide, but not other statistical analysis with other distribution table, because their shifts are almost the same, but their values combined flatter and steeper depends on the sample size. So again, that's the discussion for the next few weeks. So don't worry about it. But I'm talking about Z table is unique because regardless of sample size, it always had the specific Z value and P value. So as long as you know Z value larger than 1.96, but you go back to the normal distribution table, it's the 0.05. So you can reject the null. Even bigger than that, you know, like 2.58, and in the normal distribution table, that's 0.01. Okay, so if you see Z value is larger than that, you can reject null hypothesis because your p-values are in that critical region, not in the body. Okay? So that's how you can make a decision. So it's more of repeating what I just said, right? So either z-value or a corresponding p-value, and that is less than, okay, or your p-value is more than 0.05, you fail to reject null, and your statistic analysis is insignificant. But if you have a larger z-value and smaller corresponding p-value, that means you reject the null hypothesis and thus prove your alternative hypothesis that assume changes, differences, and relationship that we say in statistics, it is statistically significant. You heard that a lot, right? Okay, so any questions so far? Any questions so far? I know it's like a big, again, conceptual bridging that how we do hypothesis tests as what we just intuitively, why can we test not alternative hypothesis, which is what I want to prove, using just to find the probability of that. Why can you do that? Yes, we can if we want to, but statisticians and statistical software, how they run, they preset. They're just simply running null hypothesis and provide you the probability, and we want to see small probability for that, and thus it's not something likely to occur, and thus we can approve what we wanted to see as a real hypothesis, as a change, as a meaningful thing. Okay, so you can question it, but it is more of the pre-assume and determine the procedures of hypothesis testing. Sorry about that, but that's what it is. And so, for example, like a practice, quite the quiz and even the exam, we are thinking about mostly it's just how to get and pull down some number. May I just ask you just one step? Knowing z-value and find out p-value, and knowing p-value, what is your statistical decision? That's some mostly logic I'm going to ask you rather than calculating some specific values. All right, so that's something I want you guys to understand the definitions and logic, so why they are doing it. This is really how you understand the foundations of statistics. Okay, so since we are covering big foundations of statistics, and let me maybe take maximum about 10 more minutes, and then I will let you ask me question or just digest information. I will stop there before we move on to further, a discussion regarding hypothesis test. But it might be a good logical discussion we can do. Think about it. We use a sample to test the hypothesis to understand our population of interest. There's always a chance we make mistake, right? Okay. So in the hypothesis testing, there's a two sets of error. It always comes with whatever you do for hypothesis test, there's always two types of error you can make, a mistake you can make. So for example, think about it. In real world, your null hypothesis is correct, but in your hypothesis analysis, you reject it. That's a mistake, right? That's a type 1 error. If you just try so hard, but it didn't make it, And your hypothesis, your null hypothesis, actually, it's pretty much a false statement, but you fail to prove its force, then it's a type 2 error. Okay, so sometimes depending on the sample size, sometimes depending on your hypothesis itself, we can make a mistake, either type 1 or type 2. That's something I want you guys to understand. And so if you try too hard to not to make a type 1 error, you are more likely to make a type 2 error. If you try so hard to not to make a type 2 error, you are more likely to make a type 1 error. Okay? So that's how it is. That's how it is. So just let's think about logically. Again, do not try to just memorize it. Just let's think about it. As academic scholar, you do hypothesis test. You are so eager to falsify your hypothesis. So make sure, like a new method or a new medicine, it should work. It should work. You are so eager to make that happen. Somehow that's not working, but you just try to make it so hard, you make a type 1 error. So in order to minimize, not like inversely increasing the risk of either type 1 error versus type 2 error or versus opposite, the best way to reduce the probability of type 1 error is just to be more rigorous and more conservative on alpha level. So rather than having the alpha value of 0.05, if you shrink that critical region to 0.01, okay, there's a smaller area you can reject null. So you are less likely to reject null hypothesis. It is still true, right? So that is a way you can save not to commit type 1 error. And type 2 error, in order to minimize the chance to make a type 2 error, is increasing sample size. Okay? So most of the case, you fail to reject the false null hypothesis. The main reason is you don't have enough evidence. So as long as you increase the sample size, you have more evidence to detect the false null hypothesis. So you're more likely to prove your alternative hypothesis. So that's one solution to not to commit type 2 error or minimize type 2 error. Okay? That's what you can do. So just one more slide and I will just let you rest and digest. Okay? So let's just think about this Z normal Z normal formula. I will tell you, this is a basic form. If you do how complicated your statistical analysis go, statistical formula, it always go with what you're testing as a numerator. Again, it's not mathematical formula. That's what statisticians, they try to measure. What you try to measure here, now for z-test here, how your sample mean is different from population mean. If you compare like male versus a female, now like t-test, they put male mean versus the female mean in a numerator. Okay, so it's the same kind of a thing you measure. What you're measuring on the numerator top, and then any kind of the error, standard deviation, standard error, any types of error, it goes to denominator. Okay, but do you remember about standard error? The standard deviation divided by square root of sample size. Okay, so think about it. If you increase your sample size, you minimize the error. So you minimize your denominator. So overall, your value of statistical score gets higher. your statistics score gets higher means you have a small probability for null hypothesis. That's how you reduce type 2 error. You got that? It's logical, pretty much it's logical. Okay, so again, this is only for Z formula, but it's identical to all other statistical analysis. T-table, t-test, f-test, and whatever test you do, if you increase the sample size, decrease your error, decreasing sample, error, increasing your statistical value, and thus minimize probability for null hypothesis. That's the logic. Identical, universal, regardless of any statistical analysis. Okay, so since we are completing this, so if you have a larger, gaps between your comparison, or there is a larger, effect, what statistics do they put as a numerator? There's a larger, discrepancy. What you're measuring, and your statistical value is large, and you are more likely to prove your alternative hypothesis. Okay, and also that's all statistical analysis they do. You want to see more change, larger value, and more strength in the relationship at most of the time as a numerator. If it is big, your statistic values are high and p-value is low. So reject the null and accept the alternative hypothesis. Okay, so that logical connection, I think you need the time to digest. So from now on, what you're gonna do is read chapter 8. If you wanna visit chapter 7 again, please do so. That will be very helpful. Okay, so I will stop here today. Okay, to let you digest. Okay, and then on Thursday, come back with, okay, so, all right, so this is the logical decision, how we do from writing hypothesis, set the alpha value, and test statistics, and then depending on the statistic p-value and alpha value, we make a decision. And based on that, we have always a chance to make a statistical error, right? So digest that information and come back. And on Thursday class, before we play with SPSS and manipulating the data again, next week we actually gonna do t-test, multiple independent sample t-tests. So we really do sample statistics, but until this week, since we are dealing with the foundation, the theory, and I will show you continuously what he stopped making index and making, computation of some variable. We will continue to cover that after. What do you call that as a one-way hypothesis, one-tail hypothesis, depending on which statistical textbook you grab. So one-tailed hypothesis test and two-tailed hypothesis test. That's what we're gonna cover. First 10-20 minutes of Thursday class, and then we're gonna move on SPSS. Okay, so if you haven't read the textbook chapter 8, please read before Thursday class, and then you will gradually digest this information. But before I let you go, Lee, any question you have? Any question?
I can't think of any.
Okay, great. And so I hope you drink more warm water, recover fully. All right. So I know this is like very logical, but once you go back, why did you do that? I was very upset when I'm learning all this, those steps. Why we use a null hypothesis? I was furious why all the statisticians they made that decision. Why they preset statistical analysis, statistical software set in that way. All right, but this is how they done, and the number you're gonna get any statistical analysis, it's gonna be based on this logic. Any p-value is about null hypothesis. So we will be super happy to see small p-value, usually less than 0.05, 0.01. So that means you have significant statistical analysis proving your alternative hypothesis. So make sense of that, and we will continue our discussion on Thursday. Thank you so much for your attention today. And do not get sick. I know. I hope my voice get better for Thursday class. But I'm glad that we are away from each other through screen, so I'm not spreading any germ or virus. But stay healthy, and I will see you on Thursday.
Thank you.
All right. Have a
Thank you.
nice afternoon.